By playing with the spinners, I notice some unusual things. When I leave it, it will fall down. But when I spin the spinner and leave it, it is not fall down, it is rotating. This is known as the gyroscopic precision. Let's look what is the physics behind this. Suppose that I just reconstruct the whole things in my imaginary world. There is a string, there is a rod, there is a wheel, and suppose that this wheel has an omega, that is the rotational angular velocity in this direction. It is rotating, and I placed it in an non-gravitational field, that's why it not fell down. My first goal is I need to find the angular momentum of all the systems about this point. This is I taken as origin. So how can I find? Yeah, we know that the angular momentum will be equal to m times r cross v. Yes, this is the origin, and if you take a small particle here, it has a velocity of v in this direction. Then I take a r from this origin to this v. So it's like this. This is our r, and if suppose that this particle has a mass of m, then the angular momentum of that particle will be equal to m times r cross v. But there is a lot of particle, so I need to take the summation of all this particle. I need to add the angular momentum of all that particle. But that is one of the most messy thing I have ever seen in my life, and that is one of the most burden thing to find out the summation of all that angular momentum. So what should I do? How can I reduce that burden? There is also a burden, but how can I reduce that? Let's suppose we have divided this r as two components. One is the parallel component, that is, it is parallel to this rod. I taken as this and named it as r parallel. And this one is the perpendicular component of r. I named it as perpendicular. So I can write the angular momentum as two components. One is due to the parallel and other one is due to the perpendicular. Because I know that the r can be written as r parallel plus r perpendicular. So r cross v, I can just write in like r parallel plus r perpendicular cross v. You know that this is a distributive property, so I can just write like r parallel cross v plus r perpendicular cross v. This is the two components, so I can write this also as like this. That's why our angular momentum can be represented as angular momentum due to the parallel one plus the angular momentum due to the perpendicular one. Let's suppose that this wheel has symmetry. That means that if I take a particle here of mass m, then there is the same particle of mass m and the opposite end and has a velocity same as in the velocity of this particle v. Let it take as v. Then how can I find the total angular momentum of all particles in this wheel, of the parallel ones? How can I find? Let's take the parallel one. This is r parallel and it is its velocity. So if you draw the diagram, then this will be the velocity and this will be the r parallel one, r parallel. Then curl your fingers in this direction of the right hand and your thumb will point in the downside. Here also the thumb in downside, that means that the angular momentum is in the downside due to the parallel ones. And here you can see that this is our velocity component and this is our parallel component, our parallel velocity. If you curl the fingers in your right hand in this direction, then the thumb points in the up direction. That means that the angular momentum in this direction and in this direction are same, but in the opposite direction. That will cancel each other's effect. Similarly, if you take a particle here, there will be opposite particle here which have the same magnitude of the angular momentum but in the opposite direction. So they will also cancelled. Here also there will be opposite particle that will cancel. So if you take any particle, there is an opposite particle that will cancel each other's effect. So what's the value of this angular momentum? If you take the summation, what's the value? Yeah, it is simply 0. Nothing left. All are cancel each other's effects. But what about the perpendicular component of the angular momentum? How can we find that? That needs some more brain. Look at here. This is our perpendicular component. And if you place this component here, And if you take any other particle here, it is moving with also the omega in this direction. That's why it has a velocity in the upward direction v. What about the r perpendicular? Yes, this is the r perpendicular here. R perpendicular. And if you take any other particle here also, this will be the r perpendicular here. So what is the property of all this r perpendicular? This r perpendicular is actually the radius of this wheel. So if you take the summation, I can write like m times vr. This r is a constant, that is the perpendicular component, but that is the radius of this wheel. And if I take the summation of this, I can write just simply as I omega, because it is angular momentum of this wheel about this point, this origin. So this is the moment of inertia that about this origin of this wheel. This is how we can find the angular momentum of this perpendicular component. This perpendicular component is only existing, this is not existing. So I can write the angular momentum as angular momentum of this perpendicular component only, and that will be equal to I omega. But what is the direction of this angular momentum? For finding that, the curl your fingers in the direction of the omega, then the thumb represents the direction of the angular momentum. So the angular momentum's direction is same as the direction of these are parallel ones. Now the original hero's entry, that is the gravity. Dun, 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 dun. If the gravity is there, then all particles in this wheel and in this rod have force in the downward direction. So if this is a point as a center of mass, then this point has a force in the downward direction as mg, where m is the total mass of this whole system. So it is away from the point of origin. That's why if you take this distance as r, then r cross mg will be the torque acting on this system about this origin. What is the direction of this torque? Yeah, this is the force, it is in the downward direction, and this is the r. If you take the r here, and this is the angle, and if you curl the fingers of the right hand in this direction, then the thumb points perpendicular to this rod towards this direction. So we know that the change in the angular momentum will be equal to torque times the change in time. So this much momentum, the angular momentum, is given to this one, and this is the direction is perpendicular to this rod, and we know that the angular momentum's direction is parallel to this rod. So both are perpendicular to each other. That's why what should be the new look of this wheel? What should be the new angular momentum? This if it is the previous angular momentum, and if you give more angular momentum in this direction, if just a little bit, this t dot dt, then the new angular momentum will look like this. How can we represent that thing? This is the idea of representing that one. The wheel is just rotated like this. Will the torque stops? No, it has torque again. In this downward direction it is mg, and this direction is the r. So again the torque will be perpendicular to this rod towards you, like in this direction. This direction is towards me, okay? And we know that the angular momentum's direction is along this rod in this direction, the angular momentum. So again the torque acting is perpendicular to this angular momentum. If you draw the diagram, then this is the torque, this is the change in the angular momentum. If we given like dl is equal to torque dot dt, and this is the previous angular momentum L dl, then this would be the new angular momentum, giving the summation both of them. And that's why the wheel is again rotated in this way, because the angular momentum is changed. That's why our spinner is rotated in that way. Every time there is a torque, but the torque is perpendicular to the angular momentum. That's why when the angular momentum change, then the torque again will be perpendicular to the angular momentum. And again the angular momentum change, but the torque is again perpendicular to the angular momentum. And it is change. It is rotated like a circle, like a uniform circular motion. The centripetal acceleration here is act as a torque, and the velocity here act as an angular momentum. But in this point, I am giving a question that why should it rotate like this? The only condition is the angular momentum should be in this direction. That is, again I was rotated like this. So the angular momentum's direction is also rotating like a circle. That's the only condition. So it can rotate it in this way or that way. Why should it always rotate it like this? What's the behind scenes of this thing? Let's look. Suppose I have 4 bolts and I glued each one to one another, and I give a momentum to all of these particles in this direction, in this direction, in this direction, in this direction. But none of them are freely allowed to move because there is a glue between this all. So if this particle is trying to go in this way, this glue will pull it in this direction and this direction and this direction. So how these 4 masses will go? With what direction the velocity? How I can find that? Yeah, we need to add all this momentum because the others momentum get cancelled each other and the net momentum will only results. That's why if P is the net momentum of this system and if I divide it by the total mass, then we will get the velocity in which the system is moving. That is the velocity of the center of mass. Similarly, if I take a particle here, it has a velocity in this direction with a V and it has centripetal acceleration in the downward direction. And also it has an mg in the downward direction. There is 2 forces, mg and F centripetal. So how would be the new velocity of this particle? Yeah, well, it is moving in this direction. So it has a velocity. If there is no gravity, then its velocity should be like this. But due to gravity, there is some more component of the velocity will be in the downward direction. So that new velocity will be somewhat like this. If I take another particle here, it has velocity in this direction and it has centripetal acceleration in this direction, but there is mg also. So these particles, if there is no mg, then the particles new velocity should be like this, but due to mg its velocity gets like this. So all the particles have their own stories. They all are velocities will be different from what we have observed in the circular motion. Also these elements, these also have a downward force of mg. That's why this get a velocity in the downward direction. And this is a system of particles, this is a rigid body. That's why we need to add up all the momentums in order to get the net momentum. And if you add up all the momentum, then the net momentum should be in this direction. That's why it is rotated like this. This is the center of mass. And the center of mass velocity will be the net momentum divided by the total mass. That's why it is rotated like that. Every videos in these channels had a lot of hard work. So if you like my videos, then please subscribe also and like. This will give me more motivations to create more videos like this.